Last time we finished up really talking about sort of chapter 5 or part of chapter 5 that will be on this upcoming exam coming up on Monday. We finished talking about sort of empirical formulas, molecular formulas, how to calculate those guys. So where we're going next is actually back to chapter 3, which was like the bonding chapter, and the last little bit of chapter 3, which is we're now going to talk about basically nomenclature and naming everything. So we're going to go over the different ways, obviously, to name things, write the formulas for ionic compounds, covalent compounds. We'll also talk about acids as well in terms of how we properly name those guys. All right, so let us get into this. It's a periodic table. That's good. All right. So obviously, very helpful, right? In terms of nomenclature, is really the periodic table and some of the stuff that we talked about when we talked about bonding. I think we also probably talked about it a little bit when we talked about electron configuration and ions. And it's the idea of really the periodic table and um, the charges that certain things will form. And when we talk about charges and sort of the formation of charges, we're talking about either cations or anions. And as we've talked about before, again, cations are positively charged ions, and that does result from really a loss of electrons, while our anions are negatively charged, which basically results from a gaining of electrons along the way. And remember that we typically see that really in ionic compounds is where we get that sort of transfer of electrons. But when we do look at the periodic table, remember that everybody on the periodic table really doesn't have a charge if they're by themselves. So if they are sort of by themselves, uncombined, really do not contain a charge. But really, when we do get those sort of metals and nonmetals together, that's really where things do gain charges. And as we talked about previously, but just to make sure, get something right with here. Everybody there in group 1, when it does make a charge, will form a +1 charge, right? Everybody there in group 2 will form a +2 charge. And group 3, when we talk about it, it's really aluminum here that we see pretty much most of the time. And that guy will be a +3 charge. Again, the group 1, group 2, and really group 3 here with aluminum, those are all metals. We would expect them to lose electrons and become positively charged. And sort of going backwards up here in the non-metal region, when we get to group 5, those guys kind of go backwards. So -3, -2, and -1 in terms of the charges that they make. So these are sort of our guys on the periodic table here that have, or sometimes referred to as fixed charges, right? And no matter really what the situation is, they pretty much will always form those type of charges. And that does go back to sort of what we were talking about when we were talking about electron configuration and also more sort of periodic trends. And the reason for that, for example, as we've talked about, when we're talking about those periodic trends, when we think about something like sodium, it's got 1s2, 2s2, 2p6, and 3s1. It has one valence electron, right, which is this guy. And in terms of ionization energy, it's not going to take a lot of energy to remove that electron and cause it to make a +1 charge. The problem, though, is once we get past that first electron, we're now into those core electrons. And as we talked about when we talked about those sort of periodic trends, once you lose those electrons, obviously the thing gets smaller, the electrons get closer to the nucleus, they're held tighter, and the amount of energy required to remove, say, a second electron, something like sodium, is an enormous amount of energy, which really doesn't happen. So, that's why we kind of say these guys are sort of fixed charges. Where we're dealing with a lot of times is sort of, those valence electrons, and they will only make sort of those positive sort of charges. Now, when we talk about fixed charges within sort of the transition metal region, or if we talk about the transition metal region here, these guys have really variable type charges. And that means in certain situations, they may be sort of +1, +2, +3, +4. It depends really on sort of situation. So we see things like copper in there, which, in certain cases could be copper 1, in other cases could be copper 2, depending on the situation. Iron could be iron 2, iron 3. So for the most part, these guys have pretty much variable charges. And it also includes some of these guys a little bit outside of the transition metal region. They also can kind of do that. And it's really these guys sort of below the staircase, which are metals in these groups, and the sort of this region over here, they can sort of form fixed variable type charges. So things like lead could be like lead 2, lead 4. It has the ability to also sort of carry a variable charge. So, these are important sort of distinctions on the periodic table when we look at something as to whether or not it has a charge. Again, as I mentioned, if it's just, sodium metal by itself, it has no charge. But when sodium hooks up with chloride, that is when the sodium gets something like a +1 charge. Now, within sort of the transition metal region and this sort of variable charge region of the periodic table, we do have a few that actually are pretty much fixed charges. And that is sort of this backwards L right here. Coming this way. Zinc can be +2, and cadmium will always be +2, and silver will be +1. So this sort of L guy over here is kind of backwards L here in the transition metal region are also guys that have fixed charges. And again, zinc will always be +2, cadmium will always be +2, and silver will always be +1. So we do have these, again, sort of fixed charges here in the transition metal region, but pretty much everybody else, and again, a little bit outside of there, will have those sort of variable type charges. All right, so let's then talk about sort of what we're going to sort of cover here in terms of types of compounds that we're going to talk about. So we talked about it in terms of bonding. We talked about ionic compounds, and a reminder that when we talk about ionic compounds, we're really talking about a metal and a non-metal together. And when we do have an ionic compound that's basically a metal and a non-metal together, it's always the metal that will basically transfer 1 electron, 2 electrons, however many electrons, basically over to the non-metal. And as we talked about previously, it is that complete transfer of electrons that then creates the metal becoming a cation that's positively charged. And our non-metal, which gains those electrons, becomes an anion, which is negatively charged. And as we talked about in the bonding sort of chapter there as well, again, there's absolutely no sharing of electrons here. So no sharing of electrons. We have basically that electrostatic attraction, which is essentially, again, that sort of opposites attract, right? So our positive, negative attraction to one another. Now, that is definitely different, as we talked about in bonding, and different in terms of naming as well, how we go about naming ionic compounds versus how we name sort of molecular compounds. are, covalent compounds where, it's a little bit different of a situation. In these guys, it's really about two nonmetals together. And as we talked about with the bonding, when we get two nonmetals together, they do share pretty similar sort of periodic trends, which means they're really not going to get a transfer of electrons happening. So we're going to get no formation here of any type of ions. We're going to get actually sharing of electrons between those guys. And when they share them, as we talked about in bonding, that sharing may be equally. Which is a nonpolar bond, right? As we sort of talked about it. Or it may be shared unequally, which would result in a sort of polar bond or a polar molecule. So this, again, much like in sort of the bonding, how we sort of represent the different types of bonding here when we draw things like Lewis structures, this is, again, sort of our distinction and difference in how we go about naming these guys. So the way that we name sort of molecular compounds is definitely very different than how we name ionic compounds. And even within ionic compounds, it's different how we go about sort of naming those individual sort of ionic compounds, depending on what type of ionic compound there is. So let us get into, first off, ionic naming and the process there of going through those guys. So first off, when we name just ions itself, so when we talk about naming ions, there's basically our cations and our anions. And when we name each of these ions, when we talk about sort of ionic or ions, if we just have sort of the ions by themselves, if we have just a cation by itself, because a cation really does come from a metal, the way that we would name that ion if it was present by itself is simply use the whole name of the metal. So pretty simple. And as we saw on that last slide, we'll see it here again in a second. If we did have Na plus just by itself, just the ion by itself floating around, we would call this just the whole name of the metal, which would be the sodium ion. If we had Ba2 plus here, and just that by itself, this would be what is referred to as the barium ion. If we had H plus, that would be the hydrogen ion. Hydrogen is a little bit different. It's technically not a metal. Obviously, it's a nonmetal, as we talked about, but if sort of named the same way, if you do have it in the positive sort of form, which would be the hydrogen ion. So if we are naming just an ion by itself that happens to be a cation, we very simply just use really the whole name of the metal and basically put ion at the end of it. Obviously, if you were asked to write the formula for the cation, this is what it should look like. And what I mean by that is if you're asked to write the formula for it, for the cation, it should contain a charge. So if you're asked to write the formula for any type of ion, cation or anion, it obviously should contain a charge if you're just writing it for that one ion by itself. Anions kind of work the same way. Anions are obviously, as we've been talking about, they're negatively charged guys. And basically to name these guys, we really use sort of the base of the nonmetal name. So we kind of use the nonmetal name. We do kind of drop off the last part of it and we replace it with IDE. So we kind of drop the last part of the nonmetal name and again sort of insert the IDE. So like F minus is fluorine. Again, when we drop sort of that last part of it, it would be the fluoride IDE ion. If we had O2 minus, that would be oxygen, kind of dropping the last part there, maybe even a little bit more. Actually spell it right since we're talking about naming. It would be the oxide ion, IDE. If you had N3 minus. That would be the nitride ion from nitrogen, obviously. So anions a little bit different. They do get the IDE sort of treatment at the end. You drop a little bit of the regular name, and we do that IDE. Hydrogen as well is, again, kind of the only one that can go both ways. It can be positive, it also can be negative as well. And if it's negative, we follow the same sort of naming for it. Instead of hydrogen, we kind of drop the last part and put IDE at the end of it, and is known as hydride. So again, hydrogen a little bit different than most, can be positive, and again can be negative in certain situations. So that is the way that we name just run of the mill sort of ions that are by themselves. And again, if you were asked to sort of write the formula for the anion, just like the cation, it would look something like what I was writing there or what we see here. And again, the importance of that is it should have charges associated with it. Here we see hydrogen and we see hydride, positive one, minus one. Positive one, typically when hydrogen comes first, hydrogen comes second in the formula. After a metal is when it can be negative, but we see all of our guys here with our positively charged guys. So pretty straightforward there. Whole name of the metal, IDE on our non-metal. So let's talk about kind of putting these guys together sort of in an ionic compound. So the first type we're going to talk about in terms of an ionic compound is a type 1 compound. And when we talk about sort of a type 1 compound, we're talking about an ionic compound. It is made up of a metal and a non-metal. So again, as we talked about, what we got here is a transfer of electrons happening. So electrons heading over from our metal to our non-metal, obviously creating the metal becoming positively charged, the non-metal becoming negatively charged, as we've been talking about. So when we're dealing with type 1 compounds here, are honestly, whenever you're dealing with a metal and a non-metal together, it is always the metal that is the most important. So it is always the metal that is most important. And what I mean by that is pretty much where on the periodic table do we find that metal? And in a type 1 compound, what that pretty much means is the metal will be in group 1, 2, 3, or it will be zinc, cadmium, or silver. And what all these guys basically share in common is, as we talked about there at the beginning, they're all the ones that have a fixed positive charge. So as soon as you identify or look at something and see it is a metal and a non-metal, first off, that tells you it's an ionic compound. Secondly, when you see the metal is either in group 1, 2, or 3, zinc, cadmium, or silver, that also tells you that it is a type 1 ionic compound. And the important part of that is we basically name these guys by simply using the whole name of the metal and our non-metal gets the IDE at the end of it, like we were just talking about. So basically, we put them together, whole name of the metal and IDE on the non-metal. So again, when we look at NaCl and we look to sort of identify what is going on here, the first thing obviously that we would look at is we see that it is a metal and a non-metal. So that tells us it is a ionic compound. Then really it is the metal that is the most important. And we know obviously the sodium there is a group 1 metal, which means it's a type 1 compound. And since it's a type 1 compound, we simply don't have to look any further at that point. we just use the whole name of the metal, which would be sodium. And again, chlorine becomes chloride at the end, and we get sodium chloride. Now, a couple important things about ionic compounds, which we've, I think, touched upon, but just to officially kind of go over it and make sure everybody's clear. When we talk about writing the formula for an ionic compound, such as this, the formula for an ionic compound should never have a charge, should never have a charge. So the overall charge, when we put together something that is positive and something that is negative, we always want to put them together, again, sort of that empirical formula we were talking about the other day or yesterday, in a way that we do equals zero. Now, it's important to remember that when we look at something, for example, like sodium chloride, although the formula itself does not have a charge, it is really still made up, though, of two things that do have charges. So when we look at sodium chloride, it is made up of a cation that basically is a sodium with a +1 charge, and it's made up of an anion, which the formula for that would be a Cl with a -1 charge. Again, our +1 and -1 here gives us a 0 charge when we put them together. +1 and -1 gives us that overall charge of 0, and we get our NaCl. So sometimes people get a little confused on that. Again, the actual formulas, when you write a formula for an actual sort of ionic compound, should always equal 0, should have no overall charge. But it is still made up, obviously, of two things that do have charges, a cation and an anion. Remember that, as we talked about yesterday, pretty much ionic compounds are all empirical formulas. So the proper way to put an ionic compound together is not only to make sure you end up with a 0 charge, but it should always be the simplest way, kind of the lowest common denominator, if you will, way of getting those guys together to equal 0. So for example, if we took something like calcium and bromide here, so if we have Ca Br2, and we look at this guy again, if we look at this, calcium is a metal, bromine is a non-metal, and again, the importance here is our metal. Calcium is group 2, which means it does have a fixed +2 charge. And basically all we need to know is at that point to name it, we would use the whole name of it, which would be calcium. Bromine would become bromide, ID at the end of it, and this would be calcium bromide. Now, a couple of things about this, again, to illustrate a couple of important things to keep in mind. The first thing is, we'll just talk about this part right here, is why do we have 2 of these BRs here? Well, we'll talk about that in just a second, but one important thing that you should note is, even though there are 2 of them there, it had absolutely no effect on the name. So there was no dibromide, which people like to put prefixes and stuff in there. We don't use any of that here in this situation. We'll talk about where you should use things like that, but this is not the situation to use it. So it doesn't matter if that 2 that I circled was like a 40. I don't think you'll ever see that, but if it was a 40 or something like that, you would still just call it bromide in this situation. It has no effect on it. So that's one very common thing that people always want to do, is like, hey, I want to put the dye there because there's 2 and stuff like that. So you do not do that in this situation at all. So as long as you can recognize it as a metal, non-metal, as long as you can recognize the metal is coming from one of those groups that have a fixed charge. That is basically how you name it, regardless if you have multiple metals, regardless if you have multiple nonmetals. It's just that format, whole name of the metal, nonmetal gets the IDE, regardless of how many there are. Why is there so many or more BRs than calciums? It also goes back to what we talked about in terms of bonding as well. Our cation here is obviously, as we see, is our calcium with a +2 charge. And our anion here would actually be also another important thing. If you were asked to write the formula for the anion, it is Br minus. That is the actual anion formula. It is not Br2 minus or anything like that. It is basically Br minus. And basically the 2 means that we have not one of them, but we have basically 2 of them there. But again, if you were asked to write the formula for the anion, that is what I just boxed, which you should write. When you are asked to write the formula of the cation, that is what you should write. Again, because you're asked to write the cation or anion, they are ions and they have charges. So that's why we have the charges there. When you're asked to write the formula by putting these guys together, we got +2 from the calcium, -1 from one bromine, -1 from another bromine gives me a -2 and a +2. So when we put it together, we get something that does not have a charge, which is the formula here for this guy. So again, individual ions should have formulas when you write, or should have ions. I spit that right. Individual ions should have charges when you write their formulas. But again, when you put both of the cation and anion together, simplest way gets you to 0, has no charge. So back to the question again, just to remind you why there is 2 bromines, and it has to do with what we talked about in terms of bonding. When we look at calcium, it is group 2. It's got 2 valence electrons. Bromine, which is group 7, has got 7 valence electrons. So what happens is obviously calcium wants to get rid of an electron and it will go to that bromine there. But the problem with just laying up that one electron is that then fills up that first bromine, and it is totally filled. It then becomes bromine that now has picked up an electron and has a -1 charge. It has no more room for its second electron, and that's not good for calcium, because if calcium only laid up one electron there, if you look at the periodic table, that would just move calcium back to potassium, which is not where it wants to be, right? It wants to get all the way back to argon in terms of the periodic table. So it needs to lose another electron, which means it needs another bromine there to allow it to give away its second electron and allow this guy then to also gain, again, a -1 charge in each of the ions there. And as we talked about in terms of bonding with our ionic guys, what that essentially does for everybody there, the 1 calcium and the 2 bromines, is they all 3 have now been able to achieve noble gas configuration. The bromines go forward to krypton, and our calcium backs up to argon. And everybody's really happy because they've now achieved the same electron configuration. So again, that's really the basis, sort of what we talked about earlier in terms of bonding, as to why we talk about we put together positive and negative guys in the simplest way to get to 0, because in the simplest way to get to 0 gets everybody pretty much to that noble gas configuration when we're talking about an ionic compound. But very, very important is it has, as I mentioned earlier, absolutely no effect on the name, that number that's there in this situation. Any questions on any of that there? Okay, so let's take a look here. Move a couple things out of my way. All right, let's do that. So here it's a picture, a periodic table of some of our sort of fixed charges, if you will, and Again, we could add in there our zinc, which is +2, our cadmium, which is +2, and again, hanging a left over there to silver. These are really our guys that have these fixed charges. And as I mentioned before, it's usually aluminum here. So remember, we're going +1, +2, +3, skip 4, 4 right in the center of everything. You got some non-metals, you got some metalloids, you got some metals on the bottom. So no good pattern. And again, when we talk about -3, -2, -1, we are talking about the non-metal part here above the staircase in terms of those charges. Let's see here. All right, so let's take a look here. And so why don't you take a second and why don't you name these guys here? And while you're naming those guys, let's also do, let me give you a few here to write the formula for. So why don't we do barium sulfide? Let's do silver phosphide, and let's do aluminum oxide. All right, guys on the left there, we want the proper name. Guys on the right, the proper formula. Okay, let's take a look and see how we're doing. So again, the first thing you want to really look at is what you're dealing with. So hopefully when you see the K, you recognize that as a metal. Cl is a non-metal. So automatically know it's a ionic compound, which means always when you have a metal and non-metal, it is the metal that is the most important. And when we see the K there, we know that it is group 1, which means it has a fixed charge, which then tells us it is type 1. And really at that point, we're done in terms of analyzation here. Basically what that means is K is the whole name of the metal, which in this case would be potassium. And the Cl goes from chlorine and gets the IDE at the end of it, and this would be potassium chloride in this case. Any questions on that one there? Now, in terms of cation, anion, again, if we were to write the formulas for the cation here, it didn't ask us to do so, but the cation in this case is a potassium with a +1 charge because it comes from group number 1. The anion here is a chloride with a -1 charge because it comes from group 7. And again, that is why when we put it together, +1 and -1 gives us KCl as our overall sort of formula that has no charge there, because +1 and -1 bounces out to 0. Looking down here, we see ZnS. So Zn, which is a metal, S, which is a non-metal there. Here, zinc is the important one to look at. It does not come from group 1, group 2, or group 3, but zinc is one of those guys in the transition metal region that also have a fixed charge. And because of that, and by the way, its fixed charge is +2. Because it has a fixed charge, what that means is it is a type 1 compound. And again, at that point, that's all you need to know. So we would start rolling with the whole name for the metal, which is zinc. And the sulfur becomes sulfide, IDE at the end of it. Here again, it didn't ask us to do it, but the cation in this case would be a zinc with a +2 charge. So the formula of the cation would be what I just wrote there. Again, it has the charge because it's an ion. And the formula of the anion in this case would be a sulfur with a -2 charge. Again, +2 -2 when we put it together gives us a ZnS, no charge. Coming down here, this is actually one I think we did on the previous page, so hopefully we got this one. Again, calcium is a metal, Br is a non-metal. Again, as we talked about earlier there, the calcium is important as it comes from group 2, which tells us it is a fixed charge. And basically at that point it is a type 1, which means it is calcium and it is bromide. And again, as we talked about earlier, this 2 here has absolutely no effect on the name. And again, in terms of the cation here, as we saw earlier, it is calcium with a +2 charge. And if you needed to write the formula of the anion here, again, sometimes people really screw this up, but it should just be the basic ion, which is Br with a -1 charge. Again, no like Br2- or anything like that. So that would be incorrect if you were asked to write the formula for the anion. Any questions on that? Now, last one here, we see Ba, which is a metal, and H, again, a reminder, is a nonmetal. And that is, again, an ionic compound. Here, looking at the metal that is present, it is barium, which is group 2. So much like calcium there, it has a fixed charge. And again, that puts it into a type 1 category, which means we are ready to roll with the name here, which should be barium. And again, hydrogen, which comes second in this case, is actually the negative version of it, and it would be hydride, IDE, where the cation here would be barium with a +2 charge. The anion in this case would be hydrogen with a -1 charge. Again, if we want to go put these guys together, it would not balance, and that is why we have a 2 down here, because we do need 2 of the H minuses to balance it out. Again, basically we have 2 of these guys, which gives us a -2 and a +2 to balance out the charge on the formula. Any questions on naming any of those there? Okay. So we also obviously, in addition to being able to name all these things, if you are given a name, you do need to be able to properly write the formula for those guys. And to write the formulas for them is not too difficult, except sometimes people do make it a little bit more difficult. But always when you have sort of the name and you want to write a formula, the best thing to think about is really, especially an ionic compound, is just basically what are the 2 basic ions that are there that make these guys up, and understanding what we've been talking about, that essentially we do want to make it equal to 0. So keeping that in mind, if we just sort of dissect these 2 things, we see barium and we see sulfide. We know barium is a metal, sulfur is a nonmetal. So this automatically tells us it's an ionic compound. It automatically tells us that we should have a cation and an anion basically present. And basically barium, which is group number 2 on the periodic table, would mean that the cation here is barium with a +2 charge. Sulfide is sulfur from the periodic table. It is group number 6, which means it has a -2 charge. So again, when we put these guys together, we want to make sure we equal 0 in the simplest way possible, which means in this case, it pretty much is just one of each of those guys are needed. And we get a formula of BAS in this particular case. Any questions on that there? Silver phosphide, silver a metal. Phosphide comes from phosphorus, which is a nonmetal, again, going to be an ionic compound. When we see silver, which is Ag, again, not part of group 1, 2, or 3, but part of that sort of transition backwards L there that has a fixed charge. And the fixed charge for silver is a +1 charge always. Phosphide, which is group number 5 on the periodic table, has basically a fixed charge of -3. So when we put these together, if we just put them together right the way they were, we would get AgP and it would have a -2 charge. So we need actually 3 silvers to balance that out. And that gives you Ag3P would be our proper formula. What that basically is saying is we have not 1 silver, not 2 silvers, but we have 3 silvers here. And those 3 guys give us a +3 to balance out the -3 charge in terms of the phosphorus. Any questions on that? And lastly here, aluminum, which is a metal, oxide, which is oxygen, is a nonmetal. So aluminum, which is group 3, has a +3 charge. Oxygen is a -2 charge, which is group 6. Again, we want to put these guys together in the simplest way to get us to 0. 6 would do that for you. That means in order to get our aluminum to 6, we need 2 of them. So it would be Al2 in order to get our sort of oxygen to 6. We need not 2, we need 3 of them. It gives us the 6. And we get Al2O3. Any questions on any of those formulas or how we got them? Now, I will tell you that, sometimes people are taught, what I call, I guess, the crossover move, I suppose. And the crossover move is like you have like an ion like this and an ion like this, like we just did, and go bring that down and bring that down. And that gives you Al2O3. And you can see you get the sort of correct answer. Or even if you are starting with the formula, for example, and you want to figure out the ions that are present, you could take your Al2O3, bring that guy that way and that guy that way, and it'll give you the charges, the aluminum and the oxygen. And that does work 90-ish% of the time. So it does not work 100% of the time. So there's a lot of situations if you sort of do the crossover move like that, you will get the wrong charges and the wrong formulas and stuff like that. It does work a good majority of the time, but it's definitely not 100% of the time, that sort of crossover thing. So if you sort of learn the crossover kind of move there or do the crossover move, you should be cautious and make sure you actually look at it. Again, it's best to understand that you want to make sure everybody gets to 0. And then you always get the right formula. But if you just blindly sort of cross over, like I just showed you there, and it's very common sort of practice that people are shown, you won't always get the right answer for sure, or the right charges. So again, it's best to understand the concept that we want to balance out the charges of the positive and negative guys together. Any question on type 1 sort of compounds here? And again, also, as we can see from these names before we sort of move off, for example, we have 3 silvers here, but has absolutely no effect on the name. Again, no prefixes. We got 3 of these guys, no prefix on the name or anything like that. So again, try not to use prefixes where you shouldn't, and this would be a case where you should not use them. All right, then let us talk about the next type of ionic compound, and these are sometimes referred to as type 2 compounds. Type 2 compounds, again, are ionic compounds. They pretty much have the exact same sort of format. You're going to have your metal and your nonmetal together. And basically what that's going to mean is you're going to have, obviously, a cation and an anion, so a positive and negative guy, just like before. Just like before, and always in a metal non-metal situation, always the metal that's the important guy. And what makes this guy important and sort of identifiable as a type 2 compound is its location there, pretty much on the periodic table. This is going to be your transition metals, are just to the right of it. We talked about below the staircase. So if you remember on that first sort of periodic table we were looking at there, again, some of those guys like lead and tin and those guys just to the right also are not really transition metals, but kind of named the same way. And what ties all those guys together is the fact that they have a variable charge. So they do have a variable charge, which means, as we talked about, for example, copper in certain situations, copper 1 or copper 2, iron, like we were talking about earlier, can be +2 or +3. So how do we go about naming these guys? We go about naming these guys pretty identical to how we go about naming type 1 compounds. And basically, we name it pretty much the same way. We're going to use the whole name of the metal. We're going to do our nonmetal with the IDE there, replacing the end of it. The additional thing that we put in here when we're doing a type 2 compound that we actually do not do, obviously, in what we were just talking about, a type 1 compound, is we include a Roman numeral. So here with type 2, we use Roman numerals, and it's really important to understand what the Roman numeral means. That is a very common mistake that people make all the time. And the common mistake is they think it means how many metals there are. And it doesn't mean how many metals there are. It means what is the positive charge on the metal. So what is the actual positive charge on the metal? Is if you take just one of the metals out, what is that positive charge? That's what the Roman numeral indicates. So, for example, if we were dealing with iron, which is, we just look at the cation part of it, iron 2 versus an iron 3 ion. If we were to name this guy, because it is a transition metal and it can have multiple charges, we would call this iron Roman numeral 2 ion. Again, the 2 is for the +2 charge that is present. If we were to name this guy, this would be iron Roman numeral 3 ion. And again, the 3 is not how many there are, but the +3 charge that is present at that point. So because these metals can have a variable type of charge, when we're naming them, we're basically telling everybody, hey, in this particular case, we're dealing with the iron that has a +2 charge versus, say, the iron that has a +3 charge. Same rules apply when we write the formula for these guys. We want to make sure everybody equals 0, everything balances out. So, that's why when we have something like FeCl2, if we were to look at this, iron is a metal, Cl is a nonmetal. Again, we want to look at the metal here, and we see that it is a transition metal, which means it is a variable charge, which automatically tells us it is type 2 in this particular case. And basically what that means is you may not be able to know the charge right off the bat. And if you can't figure out the charge of the metal off the bat, the good news is you will always know the charge of what it is bound to. And what I mean by that is at this point, you may look at it and go, all right, I know it has a variable charge. What is that sort of charge? So then you would look at your nonmetal part, and we know that Cl is group 7, which means it has a -1 charge for our anion. And there's not one of them, but there are 2 of them, which means we basically have 2 of these guys. And if we have a grand total there, adding up our negative part of it is -2. That means in order to balance this out, since there's only one iron present, the iron here would have to carry a +2 charge. So our cation here would be an iron with a +2 charge. Our anion here would be a Cl with a -1 charge. And how we go to name it at this point is, again, whole name of the metal, which would be iron, Roman numeral 2 here. Again, not for how many irons we have, but for the actual positive charge that we see on the iron. And here at the end, we name it just like we did type 1, and this would be chloride. Again, we do not put a prefix in here like we didn't do before. So that 2 again has no effect on the back part of the name here. And this would be iron Roman numeral 2 chloride. And again, we use that distinction because if we just change this up just a little bit and we had FeCl3, we would follow our same sort of approach. We would be trying to figure out what is the charge here. In this case, though, we have 1 Cl minus, 2 Cl minuses, and now 3 Cl minuses, which means that is a -3. To balance it out, it has to be a +3 in this case, which means this guy, although looks very similar, would have a name of iron Roman numeral 3 and chloride here. Again, the Roman numeral 3 for the +3 charge that we see in the iron in this case. Question on that there. Now, take a second here and come up with the name for PbO2. So see what you come up with for this guy. Give this guy the name. Okay, so let's take a look at this. So this is lead Roman numeral 4 oxide. So I'm going to give you the name first in this case. So this is going to be lead Roman numeral 4 oxide. And I give you the name because there's probably a number of you that maybe called it lead 2 oxide because you decided to do the maybe switcheroo type of move. And this would be a case where I was talking about a second ago that if you just blindly did the switcheroo, you would get everything wrong because that would be incorrect in this case. So let's see why that would be incorrect in this case if you just kind of did the switch over. So looking at our PbO2 in this case, Pb is lead. It's not technically a transition metal, but it is just to the right of the transition metals. And that should indicate that it can have a variety of charges. O is obviously oxygen, which has it's a nonmetal and obviously has a negative charge. So in this case, we would not necessarily know what the charge is on the lead, but if we dissected this part of it over here, that is oxygen, which is group number 6 on the periodic table, which has a -2 charge. And there is 2 of them. Unmuted me. All right. There we go. All right. So you can see me and hear me now, I hope. All right. So sorry about that. Let me see where, let me just kind of go over it one more time here just to make sure, we're on the same page. So with this PbO2, as I was saying before, we do want to dissect it, and dissecting it tells us that we do have 2 oxygens that have a -2 charge each, and that gives us a -4 charge, and that is really how we get the lead to have a +4 charge in this particular case. Now, if you were to sort of be doing the crossover move, you would probably call lead +2, and you would give oxygen a -1 charge, which first off is incorrect for the oxygen because it should always have a -2 charge. And obviously in this case, that's the incorrect sort of charge there for the lead. So as I mentioned before, it's 90%-ish. If you just kind of cross over, you can kind of do that. It will work okay. But there is a lot of situations where if you just blindly sort of do the crossover, you definitely will not get the right answer. So again, as simple as it may seem here, just a simple adding the math up is usually the best way to go. And understanding, again, as I mentioned, we want to make sure that we end up with 0 in terms of the overall charge, and the simplest way to do that. All right. So this is, again, a table of some of our guys with variable charges. And as you can see here, really, these guys don't have variable charges. So these guys have fixed charges. So we'll just kind of cross them out of this table. But you can see pretty much everybody else has sort of these variable charges. And again, pretty much all through this transition metal region. And again, this is what I'm talking about a little bit to the right of the staircase and down. Uh, Tin, lead, antimony, bismuth, these guys have these sort of variable type charges. The one that's kind of an unusual one and sometimes does confuse people in terms of like charges and stuff like that is actually mercury. And this is mercury here. Here's the two sort of mercury ions that we come across. And the two mercury ions that we come across are mercury that looks like that and the mercury ion that looks like that. And oddly, the one that has the most twos, the two on top and the two on the bottom, is actually mercury 1. So oddly, the one that has the most twos is not mercury 2, it's actually mercury 1. And the one that actually just has the 2 up on top in terms of the charge is mercury 2. And that's because mercury 1 comes as a dimer. It's basically kind of not drawn correctly here, but kind of like two mercury 1s hooked together, basically. So that's why it's a +2 charge overall, because it's basically two 1s together. And why there's a 2 on the bottom, because there's two mercury atoms together. And that's why it's kind of odd that it has the multiple 2s, but it's actually, so I guess the way to remember that is the one with the multiple 2s is mercury 1. And the one with only 1 2 is mercury 2. How do you know, which one's which in a formula? Well, typically speaking, for example, this is mercury 1 chloride. This is mercury 2 chloride. And the difference is the mercury 1 has that 2 on the bottom usually. So you can usually see that 2 on the bottom there. Not 100% of the time, but no 2 on the bottom here. That's sort of how you could kind of distinguish as a mercury 1 or mercury 2. That kind of extra 2 kind of pops up a lot in the formulas, obviously. And that's sort of your distinction as to you're looking at sort of mercury 1 in that particular case. Any questions on that there? It's got pretty messed up. So it's got pretty messed up. But what we're looking at here is, I believe, sort of the old school, new school type of way. So for our class, what we would be looking at is something like this, which would be chromium Roman numeral 2. This would be chromium Roman numeral 3. And this is the way we would name it. It's sometimes referred to as the systematic way of naming. And we will use sort of these charges as opposed to here where we would call this iron Roman numeral 2, iron Roman numeral 3. A common name that is sometimes used for this is more of a kind of root name, if you will, kind of origin name, where this would be known as ferrous and ferric. Kind of the older school name, just like here's copper 1, I believe. Copper 1, and this is copper 2. And sort of the common names for this guy, copper 1 would be cuprous and cupric. And sort of that older school way of naming. So we won't use the common names here. You should use the always Roman numeral names, but they do pop up sometimes. In case you're curious, sort of what is the difference between that other than a sort of the origin name, of where the sort of name for those metals came from. The ick is the one that has the larger positive charge, and the one that ends in OUS is the smaller positive charge. So for example, if you look at copper 1, it ends in cuprous, OUS. The one with a +2 charge ends in ic, cupric. Same thing with iron. Iron 2 with a smaller charge, ferrous, OUS. The guy with a +3 charge ends in ic. So we won't use the common names at all in here. We will strictly use the Roman numerals, but it's a good thing to sort of know because occasionally, especially with things like copper and iron, people, sometimes in literature and things like that, they like to use sort of the common name for those things: ferric, ferrous, cupric, cuprous. They use it a lot. But here, strictly, we'll go with the type 2 with the Roman numerals, and that's how you should name it on quizzes, exams, and all those kind of things. So let's take a look at some here. Why don't you give some names, and let me write some names and can write some formulas here to make sure. Let's do iron, 3 sulfide. Let's do chromium 2 oxide, so chromium 2 oxide, and let's do nickel 4 nitride. All right, so guys on the left, let's do proper names. Guys on the right, proper formulas. Here to see how we're doing. So same approach. We see CO and Cl. So CO is cobalt. That's a metal. Cl is a nonmetal. Again, the cobalt here being of importance is in the transition metal region, right dead center almost. And that tells us automatically it's probably a type 2. It should have a variable type of charge, which means, we might not know right off the bat what the charge is. So that means we should look at what it's attached to, because we should know what the charge of that is. And we see Cl, which is group 7. That means it is a Cl with a -1 charge. And there's not just one of them, but there are 3 of them. So again, if you just visually draw it there, you could add all that together, and that gives you a -3 overall charge for the negative side. And because there's only one cobalt, that automatically tells us that the cobalt here should be a +3 charge. That's important because we do need to incorporate that charge into our name, and we would follow the same sort of rules there. So we're going to go whole name of the metal, which is cobalt. We're going to then Roman numeral A3, again, not for how many cobalts we have, but really for the charge that we got going on there. And now on the back end here, just like with type 1, it doesn't matter that there's 3 of the Cls. It has no effect on the name, and it's just going to be chloride in this case. So cobalt, Roman numeral 3, chloride. Any questions on that name there? Coming here to Cu, which is copper, also a transition metal, so it tells us type 2. Iodide is a nonmetal, so again, it is that copper there that's important. So following the same sort of approach, again, may not be able to know right off the bat what it is. But if we look up I, we see I is number 7, which means it has a -1 charge. So in this case, since there's just a -1 charge on the right, the copper in this case should carry a +1 charge to balance it out. That then works into our name of copper, whole name of the metal, Roman numeral 1 because of the +1 that is there. And the iodine gets the iodide treatment there, IDE at the end of it. Again, obviously this would be our cation, and that would be our anion, right? Looking at the last one there, SN is tin, which is a metal. Br is bromine, which is a nonmetal. And again, the location of tin here is really not in the transition metal region, but it is that kind of to the right region of it, which is named the same way. So because of that, it's in that area of lead and so forth, number 50 on the periodic table. That tells us that it is going to be a type 2 compound. Also tells us that I need to sort of figure out what is the charge going on there. So again, looking at what it's attached to, which is Br. Br is group 7, which means it has a -1 charge. There are 4 of them, which means you could literally just visually write it out so you can see it and add it up. We add all that up right there. That's a grand total of -4. That means that my lead here, I'm not lead, but my tin needs to be a +4. And again, whole name of the metal, which is tin, Roman numeral will now be 4, again, because of the charge. And even though we do have 4 of the BRs, has no effect on the name. We should not be using any type of prefix here. This would be bromide. Any question on those sort of 3 names? Okay, then obviously, much like the previous one, we want to make sure that we can go sort of the other way, if you will. And whenever you are given the name, and especially if you could identify them, as I mentioned earlier, as really an ionic compound, you pretty much just want to write the basic units and put them together to equal 0. So iron, Roman numeral 3 sulfide, iron's a metal, sulfur is a nonmetal. So the nice thing about sort of this is it gives you really the charge. So when we see iron, Roman numeral 3, that basically means that we have an iron with a +3 charge. So, we already kind of know what the charge is. Sulfur or sulfide there is group 6, which we know is a -2 charge. So again, the goal here is to put these together in a way where we equal 0. Common number between them is just simply multiplying those numbers together. That is 6. So to get the iron to 6, we need not 1, but we do need 2 of them, because that essentially will give us a +6 charge. To get the sulfide to 6, we need 3 of them, which essentially will give us our -6 charge. -6 and +6 gives us no charge overall for the formula, which is what we're looking for. And we end up with Fe2S3. Same thing down here. Chromium, Roman numeral 2, tells us that we have a chromium with a +2 charge. Again, that is what the +2 basically comes from. Oxide is oxygen, which is group 6 on the periodic table, which means it has a -2 charge. So this one, not too bad. +2 and -2 means we really just need 1 of each of those guys. So we will end up with something like this, CrO. And lastly here, nickel, Roman numeral 4, means I have a nickel that has a +4 charge because of the Roman numeral. Nitride is group 5 on the periodic table, which means it has a -3 charge. Again, putting these together, you simply just multiply those numbers there, and that's 12, I believe. So to get my nickel to 12, I need 3 of them. And to get my nitride to 12, I need 4 of them in this case. And that will give us that. Again, basically what we're saying is we have 3 of these guys, +4 is 8, +4 is +12. And we got basically 4 of these guys. 3, 6, 9, 12 minus, everybody balances out. Question on type 2 compounds, how to write the formulas, how to name them. Okay, then let's see. All right, so this is sort of a decision tree as to what we've been talking about with type 1 and type 2 compounds, which again are really ionic compounds. They're metals, they're nonmetals. They are cations, which are positively charged, and anions, which are negatively charged, that are held together by the electrostatic force. And really, as you can see, it really does come down to really the metal in that case. So the metal really determines sort of whether or not you need a Roman numeral or you don't need a Roman numeral. That's really the difference between the two. And type 2, obviously, you do need a Roman numeral. And again, it's because they can have variable charges. So you're just simply telling somebody, hey, in this case, we're dealing with the +2 or +3 charge. When we have fixed charges, you don't need to tell people sort of what the charge is. They kind of should know because it could only have one type of charge. So what we're going to talk about next is also sort of ionic bonding in a sense, and it's a little bit of covalent bonding as well. And this is polyatomic ions. And polyatomic ions are basically groups of nonmetals together that have charges. So what do I mean by that? Well, what I mean by that is if you look at, say, something like NH4NO3. When we look at this particular compound here, we actually would split it right about there in the middle. And basically on one side there, we have a polyatomic ion, which is NH4 plus. And that one nitrogen and 4 hydrogens all act as one unit and has a +1 charge. This guy over here is also a polyatomic ion. That is NO3 minus, that one nitrogen and 3 oxygen basically are all together and has a -1 charge. Now, these actually do have separate names. This guy here is what is known as the ammonium ion. This guy here is what is known as the nitrate ion. And they have special names and they have special sort of charges that go with them. And if we were to sort of put this together, we basically would use, in this case, because we have 2 polyatomic ions, and that's probably the only positive ion that you would see, we would basically just put the names together, and this would be what is known as ammonium nitrate. And it is a cation, which is this guy, and an anion, which is this guy as well. And it's actually held together by basically the balancing of charges. This should not be confused with something that we would talk about or seen before, maybe NH3. That is ammonia. No charge, different than ammonium. Not an ion ammonia. Ammonium is an ion. And we basically put these guys together and there are groups, or there are a number of polyatomic ions. I think what I'm going to do, that's actually, I'm going to stop right here. It's probably a good stopping place since we have a quiz coming up and stuff. I don't want to go too far over and stuff like that. So we will stop here for now. We will